right, guys, we're going to work on Unit 5 of the AP curriculum out of the 7 that we are reviewing here before in the 2020 reduced curriculum. And so this is sampling distributions, okay? And so real quickly, we'll talk about that issue with sampling distributions. Hopefully, you watched the first little video, Intro to Sampling Distributions by Luke from Stats Medic. I put that in there. It was only 5 minutes long, and I really liked it. It did a good connection between our experimental a collection of data to our sampling distributions, okay? And at the end of this, we'll talk about that bias component again with these sampling distributions. All right, so I'm going to quickly go through the beginning of this because we already talked about this information specifically when we did our first distance learning component with the review of proportions with inference and means inference. Okay. All right. So remembering that sampling distribution is that collection of samples. Okay. So here, remember that our proportions cannot have a parent population because proportion is categorical data. It doesn't matter the shape or the center of this categorical data. Therefore, in order for us to have that point estimate, that p hat, which is that estimate of the parameter, if we were wanting to estimate the proportion of blue M&Ms or whatever, that p hat is called a point estimate of that population proportion. Okay? All right. And so then there we talked about how you have that distribution. You have got all this sampling variability, these different point estimates. And we're going to talk about that when we discuss bias again at the end, and so on and so forth. Remember that when we're talking about the shape, outlier, center, and spread, we're pulling this, that the center of all of the p hats is what that population proportion is. So I would expect the center of all of my p hats, center of all of my samples of 50 M&Ms to be located around 20% blue M&Ms if that's what the M&Ms company says. We have 20% blue M&Ms coming off the assembly line that the population is such. Okay, I would expect these p hats, the mean of the p hats, to be centered around that population proportion. And we've talked about that spread, that standard deviation we get from that. All right, and so again, here were those symbols. Remember, it's important to understand all these symbols, and we'll review them again at the end. The center of all the p hats and that standard deviation for those p hats, how spread out they are, that variability of all those samples. Now, I wanted to point out to you also what's going on here with our formula charts that we have. Okay, so here is the first page of our formula chart that we have. We've got some of this descriptive statistics. We've talked about that, this mean and such. And then here's probability, which is unit 4, and we'll get into that. Now, on our sampling distribution, of course, here, that standardized test statistic right here, this standardized test statistic there is, our statistic minus a parameter, so our x minus the mean over the standard deviation, or our x bar minus the mean over the standard deviation of x bars. That kind of thing is what's happening there. Our p hat minus true p over the standard deviation of p hats. Okay, so there's that little component. But the major idea that you will find on this formula chart that you are using here is actually on the second page or the back. Okay, so let's take a look at this. here, if we've got one population proportion, we've got this divided into proportion and mean sections, okay? So here is for proportions, here's our one proportion, see, and there is that formula right there. The center of all the p-hats, the mean of the p-hats is that population claimed proportion. And there is the formula for that standard deviation of those p-hats, okay? All right, and then don't forget that if we were doing the difference between those two proportions, like when we were doing our inference for that, remember this is where that standard deviation, that mean and standard deviation for those two proportions is located. All right, next let's take a look at the means because we're about to go on to that here in just a second. So in our mean section, that's second here, where remember that we are attempting to have a point estimate. We are attempting to get an X bar, an average of all of your 30 times you tried to stop to get 5 seconds on the stopwatch. So your X bar is your sample's mean. Your X bar is your point estimate to try and estimate the true mean. Okay, and here is that the mean of all the X bars, the center of all those X bars would be at the true mean. Okay, and then there is our standard deviation for that. Remember how it gets smaller based on the sample size. That variability is getting smaller based on that sample size. And then, of course, for two populations, if we were going the difference between those two means, okay, and we got those samples there, see, then we would have that difference between those two means and then that standard deviation for those differences. All right, so the key is I wanted to show you where that is located here on this formula chart, okay, so that you had that knowledge and that reference to be able to find those always, and you don't have to have them memorized. All right, so let's go ahead and take those off and get going on back to here. Now, the next page is our means, and I'm not going to, again, go way into depth on this because we already have. Make sure you know the population notation for the mean of the population and the standard deviation for the population, okay? And you know that we talked about how if the population is normally distributed here, then every sampling distribution of samples, distribution of these X bars that comes out of it is also normally distributed, okay? And then, of course, we saw that that variability reduces, okay, as your sample size get bigger. Because remember that standard deviation for these X bars in this case would be the population's standard deviation from here over the square root of 2. And for this one, the standard deviation for those samples is the population standard deviation from the population over that square root of 25, see? So that's why we are getting less varied as n is increasing. All right, so we know all of that. There's our shape, outlier, center, and spread, which we already talked about those formulas. And again, just a reminder that that X bar is that sample's mean. All of the X bars that you get is attempting to estimate, that's the point estimate for that population parameter, population mean. All right, now, and then our mean of the X bars and our standard deviation of the X bars. Okay, so now remember this happening with our central limit theorem. On the previous page, we talked about how if the population is normal, then any sized sampling distribution, so any sized sample that occurs, and that sampling distribution, the distribution of those samples of size 2, or the distribution of those samples of size 25, those make normal. But let's take a look at what happens if we do not know the shape of the population or if we know it's not normal. So here is a population, individual X's. You see those individual pieces of data X? If it's uniform or skewed or something else, okay? If the individual pieces of data are not normally distributed, then let's look at what happens when we take samples, okay? You can see these sample sizes are small, not large, not quote unquote large enough. Well, look, this sampling distribution, these are X bars in here. Samples of size 2, okay? X bars, samples of size 2, and so on. Okay, these are creating a distribution that is getting closer, more unimodal and symmetric, but not yet fixed. See this severely skewed distribution? It's better and less skewed, but not approximately normal. Okay? And so, but then we know that when we have a sample size that is large enough, then regardless of the shape of the population, we have a sampling, a distribution of those X bars, distribution of those sample means that is approximately normal. And remember that is that central limit theorem. I'm surprised I don't have that written here. Okay, but that central limit theorem. So remember, central limit theorem is about the shape of the sampling distribution, these sampling distributions and the population. Okay, and so that central limit theorem is about the shape of the sampling distributions down there, these ones down here, and the population. Okay, so now what does that central limit theorem say? That central limit theorem says if n is large enough, then it doesn't matter the shape of the population. These populations can be any shape, and the sampling distributions about normal, approximately normal sampling distribution. Okay? All right, so there is that key item. Now, let's actually do some math with this and show you. This is really the key application component that you will see and that you will be tested on, okay? Not only understanding and explaining those ideas, but here's where the math comes into play. So let's take a look at this. Here we have a situation, okay, where I am showing you this is a distribution of adults running a mile. Okay, so let's say that the population average time for adults to run a mile is 6.5 minutes. Okay, and you know, somehow that's telling me that that's pretty quick. That's pretty good. Okay, so the fact that adults averaging that, I don't know about that. Okay, but anyway, the population standard deviation is 1. Okay, now then we have this distribution of samples. So actually, we're asked a question down here. The first question says, what's the probability of finding a randomly selected adult, one randomly selected adult that runs over an 8-minute mile? Okay, so here is the 8-minute mark. Okay, and here is that center of 6.5. All right, so we want to know what proportion of all adults, individual adults, are 8 minutes or higher. Well, we're going to do our situation where we have an X value of 8. 1X, 1 adult. So it is my X minus the mean over the standard deviation. X minus the mean over the standard deviation. Okay, and so now I'm going to get that area by going from that z-score up to 99, and that is 6.7%, 0.067. So this area is 6.7% of all individual adults go 8 miles or more for a 8-minute mile. Okay? All right. But look at this next question. It's different. The next question says, hey, let's not just do individual adults, let's do averages of 2 adults. What's the probability that I'll randomly select 2 adults, your mom and your dad, and that they average 8-minute mile or more? Okay? So that's different now. That's asking about an average of 2 being 8 or more. So what changes in this case? Well, the mean of these X bars is still 6.5, okay? But the variability of these means, these X bars, is not 1 anymore. The standard deviation for these X bars for all samples of size 2 is that standard deviation of the population over the square root of n, which is 0.71. See? Smaller, less variability. Okay, so then I'm going to come down here and I'm going to see X bar minus the mean of X bars over the standard deviation of X bars, because we're all about X bars of sample size 2 on this one. And that comes out to 2.11. So then you can see that to get an average of 2, to find where your parents averaged 8 minutes or more, that was actually a more difficult feat, because only 1.7% of all averages of size 2, only 1.7% of all X bars of size 2 are greater than 8, average greater than 8. All right, let's do this last one. This last one says, oh, let's take our class. Okay, let's take a whole bunch of different classes or neighborhoods, okay, adults, neighborhoods of 25 adults, okay, and we want to average their time together. What's the probability of finding X bars of samples of size 25 that are 8 or higher? Okay, so how does that change things? Well, you can see our variability is a lot less. So what happens is the center for our samples is still 6.5, okay? But that standard deviation for our samples is now the population one over the square root of 25, and that is 0.2. So our variability is only 0.2, not 0.71 or even 1. Therefore, to find an X bar at 8 is very unlikely. It's 7.5 standard deviations out there. So I can tell you right now that we're going to pretty much have a 0% chance of finding a whole average of 25. So there's a 0% chance of 0% of all of the X bars of size that are made from size 25 adults are out there, okay? So here you can see this impact of finding individual items versus a sample of 2 versus a sample of 25, and how it changes the probability of finding that result. Okay, so what can we say about those probabilities? We can say that, as n gets larger, the variability gets smaller. And so then as a result, then therefore the probability gets smaller, of finding X bars at a particular point, at 8, gets smaller, smaller and smaller and smaller to where it was 0% chance. Okay, so then all I have left is just kind of some summary, real simple, easy peasy, easy to see. Here's just some simple notation for you to see for the population means, and so the population mean and the sample mean, the population proportion and the sample proportion, the population standard deviation and sample standard deviation. So there's your notation. Okay. Now, real quickly, let me go over here. Here are those formulas again listed, okay, with the center for the samples of all p hats and that standard deviation, and then the sample for the means, the x bars, and that standard deviation. Okay, but here's one thing I wanted to point out on these two slides: the large enough. So you would have approximately normal distribution. Remember that large enough for proportions is at least 10 successes and at least 10 failures. Okay? Our 10% condition is the same. N is less than 10% of the population. This capital N is the population size. Okay? All right, and then remember for means, however, our central limit theorem, our large enough is happening if n is greater than or equal to 30, or if we are told that that population is approximately normal. Okay, remember that if neither one of those two happen, we could plot, I could say, or plot the data and check sun, somewhat symmetric, unimodal, and no outliers. Okay? All right. The final thing is something that I want to just be familiar with this idea. So let's talk about bias and variability and these estimators, okay? So look at this picture here. So this picture is showing low variability, okay? But what happens if my my p hat or my x bar is, oh, well, hold on a second. So this is showing where the data should be centered. So the data should be centered here, okay? So I got lots of data that is low variability, but all of my point estimates, all of my x bars or my p hats are way far away from the true population amount where they were supposed to be. See, I could have been biased. I could have been asking moms who live at home the proportion of times that they cook at home each night of the week. Okay? And I'm getting high proportions because I'm not asking the right people. I'm not asking everybody. I'm just asking those ones whose moms are single, who are home during the day. So they have a higher proportion of times that they cook at home. All right, so that's a high bias with low variability. Here is a good situation. We have low bias because our data is just about centered where the mean is, or the center of the data is supposed to be, and we also have nice low variability. So this one we like. That's the best situation. We're centered. Our estimators were centered where they were supposed to be and not varied. Okay. Here is a situation where we look to be pretty centered around where we are supposed to be. The data is centered in that area where it's supposed to be, but we have too much variability. We had a wide variety of answer choices, and so, how good of estimation is it really giving us? Okay, low bias, nice and centered, well, but high variability. And then here's the worst of the worst. We've got a lot of bias because we're asking, most of our data is clustered not even where it's supposed to be, and our data is very spread out. So we have a lot of bias and a lot of variability. All right, so we want low bias. Low bias is telling us, of course, that it is centered that our estimates are centered where the population is centered. So that's kind of a new thought process for that idea of bias, that our estimates, our point estimates, our sample results are centered where that population is centered. And that's what we were trying to do with our Unit 3's representative samples and such. Okay, so there is the conclusion to those sampling district, that Unit 5 review, and I hope that helps you to go through the problems that you're going to be computing and such. Use your formula chart, use these ideas here for those formulas, okay, that you have to do the computing. All right, thank you very much.